and also internally at Synac. So if this is interesting to you, definitely check us out. All right, so what are we going to be talking about today? Well, our talk can be pretty much divided into 3 different parts. So first, I'm going to be talking about a general overview of geolocation. I'm going to talk about some code, for example, how to do this in a mobile app, and then talk about some common classes of vulnerabilities that we see that might leak user information or user location. I'm then going to talk about some actual applications that are in the App Store that either were or still are vulnerable to these geolocation vulnerabilities. I'm then going to hand it off to Colby, who's going to go through a case study, basically talk about a very popular app that had a myriad of geolocation bugs that when we put them all together cumulatively, we were able to track any of its users anytime, anywhere in the world. And then finally, because we want to have some good suggestions, we're going to describe some fixes and then have a brief conclusion. All right, so first an overview of geolocation, some code, and some interesting bugs. Now, this is probably an obvious statement, but geolocation in mobile apps is pretty much the norm. Most apps that talk to the cloud or the internet have some sort of geolocation capability built in. And also users are making use of this. So the graph on the left, you can see that almost 3/4 of smartphone users have used geolocation, the geolocation capabilities of their phone or in apps. And they use this for a variety of reasons. You have the obvious stuff like navigation, health and fitness, it'll track where you run, recommendations, things like Yelp, what's good nearby. Social apps are a big one, Facebook allowing you to post or tag where you're at. There's actually apps specifically in Android that allow people to track their kids. I didn't realize this, but I guess that's a use of geo. And then commerce is actually kind of up and coming, and this is where banks or other people are basically using apps to say, hey, you're nearby our store, here's some coupons or something. So it's really, really common. So I think it's important to understand how geolocation is implemented at the code level before we go off talking about bugs and common classes of vulnerabilities. So on iOS, there's 4 basic steps to do geo. The first step is you create an instance of the CL location manager. Once you've done this, you set a delegate. Now, a delegate is just an object that has various methods implemented that the OS will automatically call anytime there's an OS geolocation update. So once you set that and your object's fully configured, you just start. This just tells the OS, hey, I'm ready to start receiving OS geolocation updates. And then you wait and you handle any callbacks that the OS calls. So for example, when the user moves, it's going to invoke your delegate, and you'll then have access to the user's latitude and longitude. So here's a brief example. This is a Swift app, because everyone's apparently doing Swift these days. And you can see the 4 steps that I mentioned. So step 1, you can see we're creating an instance of the location manager. Then in step 2, we're setting a delegate. In this case, we're setting it to ourselves. Again, this is just telling the OS that anytime there's a geolocation update from the OS, invoke this object. Step 3, we start collecting. We tell the OS, hey, we're ready to go. And then step 4, you can see a function or method. This is the delegate method that is going to be automatically called by the operating system. And inside this, this delegate method, we can then access the user's latitude and longitude. So when we compile this and run this, we'll get an app that's going to be able to track or be able to get the user's location. Now, the line that's circled in black deals with authorization, and I'm going to talk about this on the next 2 slides. So apps have to explicitly request access to a user's location. Now, this obviously makes sense. You don't want apps surreptitiously just accessing the user's location without permission. So there's 2 ways to do this in iOS 8. I'm going to talk about the first one on this side, first one on this slide, and then the next one on the next slide. So the first one allows an app to access a user's location, but only while the app is in use. So if the app is suspended or background, it's no longer able to access the user's location. So there's 2 things you have to do in order to get this kind of access. The first thing you do is set the NS location when in use usage description key in the app's info.plist file. You can see that at the bottom. Then at runtime, you request authorization by invoking the request when in use authorization method. This will generate an iOS and OS level pop-up, which you can see on the left. It's important to note that this is an OS level pop-up. If it was an application level pop-up, the app could maybe block it or surreptitiously click allow. So it makes sense it's an OS level one. Now, when the user clicks allow, from here on, the app will be able to access the user's location. But again, in this case, it's only when the app is in the foreground. Now, the second way allows the app to access the user's location always. This makes sense for things like navigation apps or others that continuously need to access location data, even if they're suspended or in the background. So again, you set a key. It's a similar key. This one, it's called the NSLocationAlways usage description. And then you invoke the request always authorization function at runtime in your app. If you do this, you'll get another OS level pop-up. Looks similar to the other one, but you can see it says that the app is always going to have access to it. If the user clicks allow, from here forward, this app will always have access to the user's location at all times, even when the app is in the background. So, as I mentioned, geolocation is really the norm in mobile apps, which is definitely a cool feature. I mean, I use it all the time. But it can be problematic if the apps are buggy and the user's location can leak. Now, this is really bad for users, but for hackers and criminals and other people, this can be good. So you might be thinking, I don't really care if people know where I'm at. And I definitely kind of had that, view as well. I'm not a terrorist, I'm not that exciting or interesting. But I really like the quote at the top there because it really shows that geolocation is a great way to figure out pretty much everything about you. So you can see the quote says that if you know someone's location and you can track their public movements, you can generate an amazing amount of detail about their family, political, professional, religious, and sexual associations. With this information, whether it's the government or criminals or whoever, they have all this information and they want to target you for any reason. I mean, this is incredibly powerful. So geolocation is, can be definitely important. Also, criminals love knowing where you're at. So there have been cases, documented cases, where people went on Facebook, waited till someone was out of town, and then robbed their houses. So I don't know about you guys, but I tweeted, put on Facebook that I'm at ShmooCon. So, that's 5,000 miles from my home. So if anyone wanted to break in, now would be a really good time. I do have a pit bull. She's really mean. She's actually really sweet, but if you're a criminal, she'll bite you, hopefully. All right, so now I'm going to talk about some common classes of geolocation vulnerabilities that may reveal users' locations. And then also talk about how anybody, you guys, us, can find such bugs. So I'm going to cover each of these in detail, but we're going to talk about insecure network comms, insecure file storage, spoofing locations, apps that use overly precise geolocation, buggy server-side APIs, which is a big one, and then also UI errors or validation issues. So the first one of the most common, is insecure network comms. So if an app doesn't secure its networking comms and geolocation information is transmitted, latitude, longitude, or even images with EXIF data in them, this can allow a passive attacker access to the user's location. So that's really not good. And again, I want to stress this can allow a passive attacker. So if someone can sniff the network or see the network comms, they don't have to infect the phone or get the user to click anything. They can just get their location from pretty much wherever. So applications should not use unencrypted comms. This sounds obvious, but a lot do. Should also not allow self-signed certificates, and it should also not forget to pin the SSL certificates. So the easiest way to find such bugs is just to sniff the network traffic. And you can do this easily with a proxy such as burp. So there's two things you need to do. First, you configure the proxy. Just burp, you double-click, run it. Pretty straightforward. And then you need to configure the device to say, hey, talk to my proxy so that I can see the network traffic. So for iOS, you set the IP address and port of the proxy in the network config settings. And then if the app is using SSL, you have to install the proxy's SSL certificate so that the app will be okay talking to them. Apple actually makes this pretty easy. If you email the device with the certificate as an attachment, iOS will detect that it's a certificate, and if the user clicks on it, it'll pop up and say, hey, do you want to install the certificate? If they click yes, then it's going to be installed in the trusted root, and you'll be able to talk to the proxy. So once you do this, you can start sniffing network traffic. One vulnerability we see a lot is that the main component between the app and the app developer server will be encrypted, SSL, and secure. But a lot of times they might be using a third-party image processing service, or there'll be an ad framework or something, and there may be geolocation information in there that's getting transmitted over insecure channels. So in terms of self-signed certificates, iOS does not allow self-signed certificates by default, but developers can and have overridden this by calling the set allows any HTTP certificate for host. So here you can see some IDA disassembly, and this app is calling this method. So at the very bottom, you can see a call to obj message send. This is how the Objective-C runtime invokes or passes messages to objects, basically invokes a method. R1, the second parameter, you can see the name of this method. So once this app calls this method, this app will now accept self-signed certificates, which means it's good for the developer. They don't need to pay for a certificate, but it also means that it's vulnerable to a man-in-the-middle attack. So if you see code doing this, it's probably vulnerable to a man-in-the-middle attack. Now, SSL pinning is an extra layer of security that helps protect against rogue CAs or social engineering attacks. Now, if an app doesn't use SSL pinning, the following scenario could allow a hacker to man in the middle of the connection. So here we see a hacker emailing the target user. The user does not have to have a jailbroken phone. The attacker's goal is basically to get the user to install their certificate. So as I mentioned, this is pretty easy. Apple makes it convenient. So if the hacker can send an email saying, hey, welcome to your new company, please install this certificate for security reasons. Users, as we all know, kind of dumb. If they click accept, the certificate will be installed as a trusted certificate on the device. And at that point forward, the hacker can then man in the middle of the connection. And if there is geolocation information that's being transmitted, the hacker will have access to that. Now, if the app was using SSL pinning, it wouldn't matter that this secondary or malicious cert had been installed. SSL pinning basically means that the application will only talk to one specific cert or server. So even if the hacker gets the user to install something, it won't matter. The man in the middle will still fail. All right, so insecure local storage is another common class of geolocation vulnerabilities. And this comes into play when the user's phone is lost or stolen. Basically, if sensitive information, such as geolocation information, is not secured, and the attacker then steals the phone or finds a phone, as long as they can boot the device and access the file system, they'll be able to access this sensitive information without even having to know the user's passcode or PIN. So unfortunately, we see a lot of apps that store geolocation in unencrypted files. This includes plists, databases, or even log files. So the simplest way to determine if an app is vulnerable is just to run filemon and then file DP. Filemon, just like on Windows, shows file I/O activity. You can basically run an app, run filemon, and see what files it's accessing. You can then go look at those files to see if there's sensitive information, such as users' geolocation coordinates in those files. Now, iOS files are automatically decrypted at boot time. So yes, those files are encrypted by default, but if the attacker can boot the device, they can access the files because iOS automatically decrypts them before the user has even entered a passcode, unless the developer opts into the data protection API. So that's where file DP comes in. DP, in this case, stands for data protection. So what you can do is you run file DP and look at the protection attributes of the file. Specifically, you're looking for the NS file protection key. Now, if this key is missing or set to NS file protection none, it means that the developer is not utilizing the data protection API in a secure manner. So again, if an attacker gets the phone, they don't even need to use or find the user's passcode or PIN. They'll be able to access the files. So iOS has the notion of user's default, which is an easy way for apps to store users' preferences. Most developers don't know this, but it's actually backed by a file. It's just kind of a special object that iOS exposes, so it's easy to save things like what color the user wants their background or language settings, stuff like that. So it's problematic when developers store sensitive information in this file because this file is not encrypted by the OS. Specifically, it has the NS file protection none attribute set. So on the left, you can see an app that's saving some geolocation information into the user's default. You can see it basically just gets an instance of the NS user's default object and then just calls set object for key. So again, it's really convenient. The developer does not need to have to worry about opening files, closing files, writing stuff to files. They can just basically treat it as a dictionary, and iOS will take care of writing everything out to file. So because of this convenience, a lot of people abuse it. And unfortunately, a lot of times we see geolocation information stored in this file. So I normally skip the disassembly and just go look at this file to see, hey, is there anything in here that shouldn't be? And if you basically go into the apps library/preferences file or directory and look at this file, that's just the easiest way to see. So another kind of bug is location spoofing. Now, this isn't necessarily a bad bug, but as Colby will show, when it's combined cumulatively with other bugs, it can lead to real-time tracking of users. So from a developer point of view, it basically, you shouldn't blindly trust geolocation data from a client because it's really easy to spoof this information. You should be especially careful if you're using this location for, say, authorization. You know, it might be a banking app that says, hey, I'm only going to let my user log into their bank when they're, say, in their home state or home country. I mean, this is trivial to bypass and gives, you know, zero extra amount of security. Also, if you're giving access to relative data that's sensitive, if the app can be spoofed, a hacker can change their location and gather a ton of sensitive information. So you should be careful for that. Lastly, you shouldn't allow the location of the app to rapidly change. You shouldn't be able to say, hey, I'm in Russia, and then 3 seconds later, hey, I'm in DC. Because then again, that indicates that the attacker is probably spoofing. And if you do allow this, you can allow for harvesting of data or trilateration attacks, which Colby will be talking about more in detail. So there's a variety of ways to find out if an app allows you to spoof its location. If you have a jailbroken phone, there's a bunch of city apps you can install, Location Faker being one, Location Spoofer, that allow you to easily change your location. You can also use Script, which is basically, I guess, like a tool that you can inject into the app you're targeting and then directly manipulate the runtime environment. The easiest way, what I usually do, is just, again, sniff the network traffic and look if it's sending any geolocation coordinates to the server. You can then just intercept these in the proxy, change them up, and see the results. So you might be wondering, hey, how do you know if my geolocation spoofing works? So say you're in DC, you're using a dating app, and it's showing you all your matches. If you then see a request going to the server with your current location and you change it, say, to Hawaii, and all of a sudden all your apps or all your matches are these like beautiful surfer women, you know, like, hey, the geolocation spoofing worked. So that's kind of an easy way to do that. This is another example of something that's not a bug per se, but if the geolocation coordinates are leaked or accessible via another bug, knowing exactly where the user is very nice for the attacker. So I always wonder, like, why does this application need to know exactly where I am? I mean, isn't 10 feet, 100 feet, a quarter mile good enough? So we see a lot of application developers just choosing the default, which is the highest level of accuracy on the device. The other thing that's important to know, at least on iOS, if you don't specify an accuracy or level of precision, the device or the iOS will automatically default to the highest level. So again, just something to be aware of. So how can you determine if an app is using overly precise geolocation coordinates? Well, again, the easiest way is probably just sniff the network traffic. You see coordinates going out, just grab those, throw those into Google Maps or something, and say, hey, is this exactly where I'm at? The other thing is you can look at the disassembly, and when you are looking at the disassembly, you should look for the set desired accuracy method. And this is the method that you invoke that tells iOS what level of accuracy you want it to collect for your app. So here we can see some IDA disassembly. The third argument to the set desired accuracy method is an accuracy constant. And in this case, we can see it's this KCL location accuracy best. Again, this app is saying, I want the best possible accuracy. And again, if you don't see this call in the disassembly, it's likely that the app or the developer just didn't set it, which again means it's going to default to the highest level of accuracy. So another common class of bugs that can reveal users' locations are server-side APIs, and this is a very, very common one. There's all these bad assumptions that we see all the time, and it's kind of sad. It seems that developers of mobile apps assume that just because their application API endpoint is undocumented, no one's going to like poke on it or hack on it. A lot of times also there's no rate limiting that's implemented. A lot of these APIs allow completely anonymous access, or worse, provide lots of sensitive information. Again, this all kind of goes back to that the developers generally seem to assume that only a well-behaved mobile application is going to be talking to these APIs. So if you can figure out what endpoints and poke on them, you might get a lot of information. So again, network traffic, easiest way to kind of figure out what these bugs are, just run the app and see what endpoints it's talking to. And then you can go poke on them. So here's a trivial example. We see an outgoing request that's going to whereami.api, and this is going to give the user's last known location, and it takes a username. So if you edit the network request, you can see, hey, does this API give you the location of another user? Now you might laugh and be like, this is a really lame example, but we see this stuff all the time. It's just like mind-blowing how bad these APIs are. So it's always good to, when you see these APIs, poke around, change the parameters, and you'll be surprised how much information you can get. All right, so the last class of geolocation bugs we're going to talk about deals with the UI of the app. So again, it's funny or kind of sad, but a lot of app developers assume that no one is going to mess with the UI or poke around below it. They kind of treat this UI as like this holy thing. It's like web developers have kind of got around the fact or assumed that, hey, doing like client-side authentication and that stuff isn't a good idea, but mobile application developers haven't quite got that. So we see bugs such as, they assume that the UI is secure, they implement client-side protection at the UI level, or worse yet, they ignore or confuse the user settings. So again, the best way to find this, just again, sniff the the network traffic, or directly modify the UI using a tool such as script. So the first example of a bug, we have this setting that says share location, and the user can either turn it on or off. So if the user turns it off, they might assume, or probably will assume, that this means the application is not going to share my location with anybody. Unfortunately, we see a lot of times where this means that from the app developer's point of view, it means that they're not going to share your location with other users, but the app is still going to send the user's location to the server. So if the comms are in any way insecure, if they forgot to pin their certs or they're not using SSL, an attacker can passively access the user's location, even though the user said, don't share my location. Another example is where the UI implements logic that should be done on a server side or somewhere else. So again, there might be a setting where the user can control the level of accuracy of their location that they share. So they might say, look, I'm okay sharing my location, but I only want it to be within a mile radius. So we have seen instances, and Colby's going to talk about this more, where that is only implemented on the UI on other people's devices. So it'll send your exact location to the server. It'll then send your exact location to another user, but then the UI of that user's device, so the app, will then round out to 1 mile radius. So obviously a hacker and attacker could either see it in transit or make the API calls directly and get the user's exact location. All right, so that concludes the kind of common classes of geolocation bugs that we see a lot. So I want to talk about some real-life examples. So these are some actual apps that did or still do compromise a user's geolocation information. So the first one is Starbucks. It's kind of funny. You don't think, why is Starbucks tracking me? But older versions of the Starbucks app stored users' geolocation coordinates in an unencrypted file called session.clog. So again, this is problematic if the phone was lost or stolen, because it can provide an attacker with a wealth of information about the user's location. Luckily, this was reported, received a CVE, and was patched, so current versions are not vulnerable. Whisper is a secret sharing app that claimed to be the safest place on the internet. Now, it had a UI bug or feature that even if the user opted out of sharing their location, this information was still sent to the app developer's servers, the API endpoints, and then according to The Guardian, this was shared with a bunch of people, including the DoD. So this is an example of a UI bug where the user might say, I turned off location sharing, why is it still sending? And Whisper might be like, well, we're not sharing it with other users, but we are sharing it with the DoD. So this is an image from the Guardian report. It's a place called Fort Meade or something. So I Googled this because I didn't know what this place was, and apparently there's some intelligence stuff going on. So I was really surprised why everyone was whispering about stuff. So in this case, I may be okay that the DoD was getting access to this information, but yeah, kind of crazy. All right, so Tinder is another example. It's a very popular dating app. I'm married, so I don't know these things. But it provided exact geolocation coordinates to the API endpoints and then to other users. This was reported to Tinder, so they're like, all right, we won't do this anymore. So then they went to providing relative locations, which is susceptible to a trilateration attack, which Colby will talk about later. Also, since it was integrated with Facebook, there were some APIs that you could call that would give some very specific information about the user's Facebook account that then you could go and tie your matches to their Facebook page. So this was publicly reported and patched, but before this, there may or may not have been some applications called Tinderizer, which would allow you to put in your username and password, and then it would get all your matches, put them on a map exactly where they were at, and then link them to all their Facebook profiles. So, not good. Well, maybe. All right, so the last app I'm going to talk about is Angry Birds. And again, this is really interesting to me because this is an example of an app that you would not think would be collecting your locations. But it turned out that it was, and that it was not securing the network comms that were being reported with the location. So it turns out that, again, this illustrates that geolocation is everywhere, even in apps that you might not suspect. And if it leaks, it turns out that people were collecting this. So that was a little surprising. I blame it on the pigs, you know, not the cops in the game, the little pig guys. So be careful there. All right, so Colby now is going to talk about an app that was vulnerable to a myriad of geolocation bugs that, when we combined them cumulatively, they allowed us to track any of its users anytime, anywhere in the world.
Thanks, Patrick. So we've talked about how these location vulnerabilities occur, but what are the real-world implications? We surveyed a lot of applications out there and decided one called Grindr was an ideal candidate, really due to its ridiculously bad misuse of geo-information. So what is Grindr? It's the largest and most popular all-male location-based social network out there. More than 5 million guys in 192 countries around the world and approximately 10,000 more new users downloading it every day. Bottom line is that the app is based completely around knowing who's near you. It's extremely popular, and it caters to a demographic that has a history of being targeted. So we figured it'd be good to take a look from a user privacy standpoint. To begin our assessment, we checked to see if there were any previously publicized vulnerabilities, and sure enough, there was. In 2012, a vulnerability was discovered that allowed impersonation of users as well as sensitive data compromise. In 2013, a graduate school paper revealed more concerns around user enumeration, impersonation, and identification. In 2014, we published our assessment, which was the first to bring up the issue of location privacy, which we'll talk about more in a minute. And then in late 2014, someone else caught on and leaked similar vulnerabilities to Pastebin, and we'll talk more about this later. So what did the developers do wrong? There's no SSL pinning in the mobile application. Geo is provided with way too much precision. Location spoofing to the server is trivial. The APIs are overly permissive, and all data was filtered at the UI level. So basically everything Patrick just talked about. The first bug that we noticed was that the iOS application didn't pin its SSL certs. So Patrick talked about this earlier, and it makes it much easier for an attacker to pull off a man-in-the-middle attack, and to sniff credentials as shown here in the screenshot. Using a man-in-the-middle proxy, we're able to take advantage of this lack of SSL pinning to examine the application's protocol in detail and reverse engineer it in order to build a custom client. Bug number 2. Upon running the app, it queries the server and pulls down a series of JSON blobs for each user nearby. And each blob is all the user's profile info. The problem here is that the distance field provides us with an extremely precise relative distance. This distance here is shown down in kilometers. It's shown down to the sub-centimeter level. So, yeah, I mean, the GPS isn't even that precise, but that's how long the decimal goes. So this opens up the possibility for our trilateration attack, which we'll talk about here in a little bit. So we reported these bugs to Grindr a long time ago, and they made some changes. Unfortunately, their changes had little effect. Looking at the disassembly of the newest iOS Grindr app, we see that location privacy is set to 10 meters of precision. The problem here is that, A, 10 meters of precision is still enough to identify where someone lives, works, or is. And B, with this setting, you're guaranteed that the result is within 10 meters of precision, not a location with 10 meters of error introduced. And so we found that the iPhone generally returns accuracies on the order of 3 meters of precision for the setting. So that's still really, really good. So random errors should have been introduced server-side and not relying on this feature. The image here shows Patrick in his office testing the app, and the location was literally within about 3 feet of where he actually was.
Thanks, Colby.
No problem. One of the bigger problems that we saw was the API just accepts arbitrary coordinates. Basically, we could say that we were in Hawaii 1 minute and Africa the next. So literally dozens of queries a second were possible for moving yourself around. So there's no rate limiting or distance limiting on our changes. This opened up the possibility of accurate and fast trilateration. So furthermore, no authentication was required to talk to these APIs, like none at all. The amount of queries and the amount of queries weren't limited. It was pretty much a dream for somebody who wanted just to scrape a ton of data. It became trivial to enumerate users and pull down everyone's profile info containing name, height, weight, age, relative distance, social media links, and even photos. So Grindr has since implemented and required authentication. However, signing up takes just seconds, and your email isn't verified. So bypassing this is trivial. So while examining the JSON data from some other users, we noticed something odd. There was a key titled show distance, and sometimes this was set to false. But distances were still in the JSON data. So it turns out that the UI level logic was deciding whether or not to display the data. In short, data was still being broadcasted to everyone, just not displayed. So with a little bit of technical savviness, it wasn't hard to kind of tap in and view it. So here you can see that it was just a toggle switch showing how it was implemented in the application. And then, okay, so we've got all these seemingly minor vulnerabilities in the app, but like, what could a real-world attacker do with it? So we decided to write a framework to leverage these bugs, like just to find out for ourselves, what's really possible. Before we go any further, I should note that the purpose of this research was not to identify Grindr users, but to help protect those who wish to remain private. That during vulnerability research and disclosure, no individual users were intentionally or unintentionally identified, and all data has been irrecoverably destroyed. So based on these bugs we found, we theorized that we should be able to track any user at any given time. The APIs are wide open, we had extremely precise geo information, and location spoofing was trivial. So how does our framework do it? First, we need to engineer the data gathering component that interfaces with the API. Based on location, we can download and parse specific data from nearby users. We're specifically interested in the distance parameter shown. So now that we're able to suck down user information and determine what users are nearby, we need a way to locate them. So to do this, we gather distances and implement a basic trilateration algorithm. Now you're wondering, what is trilateration? Trilateration is the method of determining an absolute location based on 3 or more relative distances. So if we know a user's location from 3 different spots, we should be able to calculate precisely where they are. So first, we spoof our location 3 times around a location of interest, a city, San Francisco, DC. And we query users' relative distances from each point. And due to the Earth being a sphere, distances are measured along the circumference, so we have to convert the distances received accordingly. We map them to a spherical coordinate system before we run any other calculations. Ultimately, after a lot of math, we're able to determine users' precise coordinates. So here's an example of, kind of how our script works. In the end, exactly where they are. So now that we have a way to determine location, let's run it on a massive scale and track some users. So here's some screenshots from our mappings early last year. So shown here is San Francisco and the Sochi Olympics. So just as a sanity check, you can see that all the users fall within the land masses and tend to be in densely populated areas. So we're pretty sure we got it right. So this starts bringing up some really interesting privacy issues, especially for prominent figures that may be Grindr users. What if you're an athlete, a politician, a movie star, and you're using Grindr data anonymously? You might not want the media or public involved in that side of your life, especially if you wish for your sexual preferences to remain private. It's very conceivable to think that someone could watch a specific location, such as a US Capitol or shopping centers or whatever, to determine a specific user's identity. So to test our theory, we tracked some willing users over the time span of a week. Sure enough, patterns began to emerge. More often than not, we observed that for each user, there are dozens of data points in 2 distinct locations that occurred at 2 distinct times during the day. And we could infer that these were kind of home and work locations, respectively. And so occasionally you'd say pit stops along the way, maybe the gym or the grocery store, but predominantly it was home and work. So in this screenshots here, you can see the kind of accuracy we're receiving, really down, inside of a house or at a specific location. So let's take it one step further. We know we can track you, but who are you? So first we have the geolocation information, which tends to be scary accurate. So combining public record sources such as home ownership databases for home locations and LinkedIn profiles for work locations, it became really easy to guess who works and lives in a specific area. So to validate identities, Grindr users tend to share lots of personal information as well, including name, photos, age, height, etc. So not to mention a large percentage of users linked to social media. So it was really easy to kind of narrow down who's who. We conducted tests using this method on several willing participants and had nearly 100% success rate in truly determining identities. So even if you wish to remain anonymous, which a lot of Grindr users do, we're still able to deduce the identities of these people. We disclosed to Grindr in early 2014 and stressed the urgency of these vulnerabilities. We provided technical write-ups, POCs, but in the end, they kind of refused to fix everything. And to quote them, "We do not view this as a security flaw." So we kept silent, waiting for a fix. Ultimately, with as all bugs, someone found it. An anonymous hacker posted a pastebin titled "Grindr fails to protect their users." And it was a demo that showed how to track users on Grindr, just as we've done. Fast forward a few days, and it turns out the Egyptian officials began using this leaked bug to track down and arrest gay men in Egypt, because it's illegal to be gay there. So we see these security bugs every day, but it's hard to imagine sometimes that there's a real world impact. But when you see something like this, it really drives home that specifically these geolocation bugs are really serious and should be taken seriously. So after the bad press, Grindr decided to try their hand at a fix. User settings for location data within the app are now being respected. Geofencing has been implemented in Egypt to turn off location sharing. Authentication is now required, as we mentioned, and GPS accuracy is set more lenient. But ultimately, the SSL pinning issue still exists. The APIs still employ almost zero security or rate limiting, and spoofing locations is still possible. So the end result is that you can still track users with decent accuracy and still reveal their identities. So, all right, so as a location-aware app developer, what can you do to not fall in this trap? And as for your users, what can you do to protect yourself? Users, assume that you can be tracked. Accept it as a fact and act accordingly. If you're really paranoid, drill down into the location preferences in your phone and turn off location sharing for apps at the OS level. Developers, you really need to be sure you're implementing your secure comms correctly. Use SSL, pin your certs, make sure it's right. Protect your APIs. Implement rate limiting. Make sure someone isn't hopping from Africa to London to the US. Use correct UI logic. It's not that just don't filter in the UI. Do it server side. Use secure local storage, and don't use any more precision geo than you need. Maybe to the nearest 100 feet is good enough for you. So, thank you all for coming out and attending our talk. Feel free to reach out to us. Our contact info is on the screen. Our slides are online, available as of now. If you stop by our booth, we got a MakerBot to win. So be sure to stop by and hang out. Any questions or comments?
Everyone wants to go to lunch.
Yeah, I know. Lunchtime.
Question. With Wicker. I have not. I've looked at it briefly and it looks pretty good. Cool. Hey, nice work, dude. Thanks, man.
What do you guys can sign right here? There's a crypto.